Alright, hello, greetings! This is our second set of notes from Chapter 1 on the scope and language of thermodynamics. Again, I emphasize my expectation is that you are reading the text in detail, and there's a quiz to assess you on whether or not you've read the text in detail. In these notes, we're just trying to highlight some important elements from the chapter and have some general conversations. Okay, so without further ado, here we go. All right, so next concept from Chapter 1 is that of a system. So the system is the part of the physical world that is the object of a thermodynamic calculation. So anything that lies outside the system boundaries belongs to the surroundings. The system plus the surroundings is equivalent to the universe. All right, so a system may interact with the surroundings by exchanging heat, work, and mass. So here's a sample schematic of a Rankine power plant, which we'll study later on in Chapter 6. Okay, so there's various ways in which you can define your system if you're trying to analyze your Rankine plant. Right, so I could take the entire process to be my system. Right, so here this red box is meant to indicate my system boundary. So I could take the entire power plant, so that entire process, to be my system. Or I could just look at individual units within that overall plant. Okay, so how you define your system, is relatively, can essentially be thought of as being arbitrary, but the system is the part of that physical world that you're studying or you're analyzing. Everything else is the surroundings. Okay, your system can interact with the surroundings. So a closed system, here I have this solid red box. So the idea of a closed system is that my system can't exchange mass with my surroundings. So I have a closed red box in that mass can't cross that system boundary. Okay, so closed system just means that mass, there's no exchange of mass between my system and surroundings. In an open system, so now I have a dotted red line on top. If I have an open system, the idea is that mass can cross my system boundary. So my system can exchange mass with my surroundings. Okay. In an adiabatic system, the idea is that there's no heat exchange between my system and my surroundings. So in an adiabatic system, there's no exchange of heat between my system and surroundings. Where, on the other hand, if I have a diathermal system, then I'm able to exchange heat, right? So heat's able to pass through my boundary. So in a dithermal system, I can exchange heat, or there's heat exchange between my system and surroundings. In an isolated system, we say our system's isolated if our system can't exchange heat, work, or mass with the surroundings. So a system is isolated if there's no exchange of heat, work, or mass with our surroundings. Simple system. So a simple system is one that has no internal boundaries. Okay, and so it could be that I had some composite system in which I had a boundary separating some gas A from some gas B. All right, and maybe that boundary is fixed. Maybe it moved so that those two systems within that total combined system could exchange work. All right. Anyways, a simple system is one that has no internal boundaries, and thus allows all of its parts to be in contact with each other. A composite system, on the other hand, is compared to a simple system. Right? There could be a physical boundary. Right? So this is where I can define my system as being, composed of these two, distinguishable phases, say, within my system. Okay, so think about a system at vapor-liquid coexistence, right? In a beaker. I could take that entire beaker to be my system, which is contains two distinguishable phases. Okay. Cool. So in a composite system, I have my system, right, is made up of two or more, distinguishable phases separated by a boundary. Okay, maybe a phase boundary, maybe a physical boundary that I've added. What be it? All right, equilibrium. Okay, so mechanical equilibrium. So if I have two phases at coexistence, okay, Mechanical equilibrium means that the pressure of the two phases are equal. Okay, so if I have two phases at equilibrium or coexistence, mechanical equilibrium tells us that the pressure of those two phases are the same. If the pressures weren't the same, right, then those two systems or those two phases would exchange mechanical energy, would exchange work until the pressures became uniform. Okay, so mechanical equilibrium assumes that those two systems or phases in contact are at the same pressure. If they weren't at the same pressure, then they would exchange work, so say in the form of PV boundary work, until the pressures were the same. Okay, so as an aside, so if I have a pressure gradient, right, then that's what you study in fluid mechanics, right? So systems away from mechanical equilibrium, right, corresponds to fluid mechanics, right? Thermal equilibrium, so if I have two systems in thermal equilibrium or two phases in coexistence, thermal equilibrium means the temperature of those two systems are the same. If your two systems are not at thermal equilibrium, so if you have two systems in contact that are at different temperatures, then they will exchange heat until the temperatures are the same. All right, if I have two systems not at the same temperature, that's a study of heat transfer. Okay, and that's a very important fact. I remember having a student once that told me that he was taking heat transfer, and heat transfer was the same thing as thermodynamics. All right, and that's not the case, right? Heat transfer would be I have a hot object in contact with a cold object. And what I'm looking at in heat transfer is the evolution of the temperature gradient in that system as a function of time. All right, because what will happen is if those two systems are allowed to exchange heat, they'll exchange heat until the systems have the same temperature, right? Until that temperature gradient is just zero, right? Until the temperature is uniform throughout. In thermodynamics, we're interested in that system in the infinite time limit once those two bodies have exchanged sufficient heat so that they're at the same temperature. Okay, so thermal equilibrium means an equality of temperatures. So that's a study of heat transfer if you're away from thermal equilibrium. Chemical equilibrium essentially tells us that the chemical potential of the two phases in coexistence are equal, or that there's no net conversion of one chemical species to another if we were dealing with reactions. But chemical equilibrium typically means, in our context of thermodynamics, that the chemical potential of the two species are the same. The chemical potential or molar Gibbs free energy, if we're talking about pure component systems like we are in this course, that the molar Gibbs free energy of those two phases are the same. You can think of it in chemical potential, all is the same. If you had two systems in equilibrium or two phases in equilibrium and the molar Gibbs free energy wasn't the same, then they would exchange mass until they've reached that state of equilibrium. And so, for systems away from chemical equilibrium, that's your study in your mass transfer course. Okay. So mechanical equilibrium, equality of pressures; thermal equilibrium, equality of temperatures; chemical equilibrium, if we're dealing with pure component systems, equivalence of molar Gibbs free energy. When we start talking about mixtures, which we won't in this course, then it's an equality of the chemical potential of each component in each phase. And for a pure component system, molar Gibbs free energy is the same as chemical potential, so you could use them interchangeably if you wanted. All right, so I want to introduce the Gibbs phase rule. Okay, so now the Gibbs phase rule we won't derive, and it won't be introduced in chapters 1 through 6 of this text. Right, where it's introduced in the text is in the second half of the book when we start to deal with mixtures. I want to introduce it only because, well, one, in this chapter, there's this emphasis on, for a pure component system, all I need to specify is temperature and pressure, and the state of my system is fixed. Right. So I just want to give an equation that gives you that important result. But then, it's useful when I start to think about systems at vapor-liquid coexistence, and we start to think about the steam tables, to try and take inventory of how many independent variables do I have, right? How many properties can I specify before everything else is fixed? Okay, so I want to introduce the Gibbs phase rule, and then we'll talk about it in the context of this course, where again, in this course, remember, we're only dealing with pure component systems. Okay, so the Gibbs phase rule formally tells us the number of intensive properties that must be specified to fix unambiguously the state of equilibrium of our system. Okay, so it's equivalent to, so the number of independent intensive properties is equal to the number of components minus number of phases plus 2, or the way it's typically written is F equals n minus pi plus 2, where n's the number of components, pi's the number of phases, and then 2 is 2. Okay, so now in this course, we are only going to be dealing with pure component systems, so n will always be 1. Okay, so if I have a single component, single phase system, so single component, so n is 1, single phase, pi is 1, then the number of degrees of freedom is 2. So this is where the book says, if I have a single component, single phase system, my system is specified with just temperature and pressure, right? So all I need to know or specify is temperature and pressure, at which point everything else is fixed, right? That's great. So typically we use temperature and pressure to characterize our system because they're physical quantities I know, I understand, and I can readily measure. Okay. So besides pressure, volume is sometimes used, right? So you might sometimes use temperature and volume to characterize your system. So typically it's either T and P, which is, say, most common, or T and V, temperature and volume. Okay. Motivation being is there are two sets of parameters or variables that I physically understand, I know, and can measure. Now later on, we'll also deal with systems at two-phase equilibrium. So we'll deal with saturated water, water at two-phase coexistence. Right? We'll always be dealing with single-component systems in this course, but we may have a pure component system at two-phase equilibrium. So water vapor at vapor-liquid coexistence. And so, the only reason for getting this in the context of Gibbs phase rule is for that case, n is still 1. Now pi is 2, right? And so what happens is if I have water at two-phase coexistence, I have a single degree of freedom, just 1. And so what that tells me is I just need to if I specify just temperature, then the state of my system is fixed. Or if I specify just pressure, the state of my system is fixed. Now this will make more sense later on when we solve problems involving vapor-liquid coexistence and we have to go and look in our steam tables. But I just wanted to introduce it here, right, to try and address it early on, and then we'll reemphasize it later. But basically for this course, what you need to remember is we'll always have a single component system. So if I have a single component system in a single phase, I have 2 degrees of freedom. So if I specify temperature and pressure, my system is fixed, right? I need 2 intensive variables to characterize my system. If I have a single component system, but now in 2 phases, vapor-liquid coexistence, I have just 1 variable that I need to specify, 1 intensive variable. If I specify, say, temperature, the state of that system is fixed. All right, that's why we say, water at 1 bar or 1 atmosphere, right? It boils at 100 degrees C, right? Once I specify pressure, right, temperature is known and fixed. All right, so again, pure component system in a single phase, I have 2 variables I need to specify. We'll often say temperature and pressure, or that's what's emphasized in chapter 1. Why? Because they're physical quantities I know and can understand. Okay, know, understand, and readily measure. All right. So last concept is talking about processes and path. So as we just said, if I have a single component, single phase system, I have 2 degrees of freedom. Right? So my system is fully characterized with 2 intensive properties. Pressure and temperature are often 2 of our favorites because, again, they're physical quantities I know and understand and can readily measure. Right? V is often sometimes used in terms of P, but same idea. And so the idea being then is if I need to calculate the change in some property and going from some state A to state C, right, I can represent that on some P versus T coordinates. Okay, so if I want to calculate the change in heat or the work and going from state A to state C, I can represent that on in terms of PT coordinates. All right. All right, so I've got my process or my path represented on my PT surface. Okay, And so I can, connect at it from a series of states, where for each state I could determine pressure and temperature, or characterize it using pressure and temperature. All right, so here's my path going from A to C. Okay, we can also introduce this concept of an elementary path. So what's meant by an elementary path is when I go from A to C, okay, so each step along this path, both temperature and pressure are changing. The idea behind an elementary path is going from, say, A to B, right? Temperature's changing, but pressure is remaining constant. So I need two variables to characterize the state of my system. Okay, in this path going from A to C, both variables are changing along that path. In an elementary path, I keep one of those variables fixed. So I can construct an elementary path in which I go from state A to state B, in which I only change temperature, but P is held constant. Okay, so an elementary path, I change just one of the two variables. Right, only one variable changes. And then I can have a second elementary path in which I go from B to C, okay, where now P's changing but T's constant. Okay, cool. So my elementary path, I'm only changing one variable at a time. Okay. We'll have a lot more discussions once we talk about our first and second law about path and processes. Okay, but in general, this path and going from A to C, both of my variables P and T can change at each step along the way. In an elementary path, I would keep one fixed. Okay, last concept, so quasi-static process. So now if I'm thinking about this elementary path, or elementary process in which I go from A to B, if I do it in a bunch of very, very small steps. So if I change the, if I go from A to B in very, very small steps in which at each step, temperature is changing by some very small amount, right? The idea is that my state can remain in a state of equilibrium throughout. So in a quasi-static process, okay, the idea is, and so if I go back to this one, right, in my elementary process, right, I could go from A to B, and when I go from A to B, I'm going to be exchanging heat with some bath. So I could have some, or not a bath, I could think of it as my surroundings. So I'm exchanging heat with my surroundings. My surroundings, or I can have some thermal bath at some high temperature. So my system will exchange heat with that reservoir until it reaches that temperature of, state B. Okay. So what we're trying to do, with this quasi-static process is, have the temperature difference between my state and that bath to be very, very small, right? So that the idea being is that I have some bath which the temperature is T plus some small delta T. I exchange heat with that bath until I reach that new state here, and so then I increase the temperature of that bath by some T plus delta T, right, until I reach that new state. So the idea being is that I'm going to change my temperature and going from state A to state B in some, you could think of it as a slow gradual process, where the idea being, right, that I can construct this quasi-static process in which my system remains in a state of equilibrium throughout. Okay, so the idea being, or concept of a quasi-static process, is that in this case, I'm changing my temperature, or I'm exchanging heat then with my surroundings in such a way that my system remains in a state of equilibrium throughout. Right? Again, as compared to just taking some cold object, contacting with a heat object, so I have some large temperature gradient in which I'm going to be, displace them from some equilibrium until finally I'm able to equalize those temperatures in that final state. So in a quasi-static process, I'm constructing this change in such a way that my state can be assumed to remain in equilibrium throughout. Okay. In a quasi-static process, when a process is conducted, in a quasi-static fashion, it's reversible. Okay. So that's it. Okay. Hopefully that makes sense. Hopefully, between that and the reading, you have a firm grasp of, chapter 1. Take a look at the example problems, work through the example problems, take that reading quiz, work through the quantitative problems, and then hopefully after that you can master both and be ready to move on to Chapter 2. Okay, let me know if you have any questions.